Okay, so this is lesson 27 of mathematical methods for year 11. Okay, so this lesson will continue on some revision on probability, right? So let's have a look what we have learned in year 10, but now we're going to use some new notations, new ways of representing the probability. Okay, so first we need to define some terms like sample space. You probably have learned that in early years, right? Sample space means a set of all possible outcomes. Okay, sorry, I think I need to write that outcomes. Okay, events is a subset of the sample space, and in probability normally we're looking for events, probability of certain events. But for the probability of certain events, you need to understand in what sample space the events in. All right. Okay, so I give you some example. For example, the sample space for if you are throwing a die, then the sample space. The book uses epsilon as a symbol. I use U, so both are alright. Okay, both are alright. Okay. So the sample space will be 1, 2, 3, 4, 5, 6. They are all possible outcomes. So an event will be a subset of the sample space. For example, if the events are an even number, then the event is represented by 2, 4, 6 as a subset. Alright? Okay, so there are some examples. I'm not going to go into detail now. Okay. So if we know what to mean by sample space and what to mean by events, then the definition of probability of certain events, you just use the number of okay, let me show you. So there's number of elements in the events divided by number of elements in the whole sample space, right? So it's just a fraction. Okay, the number of elements in event divided by the number of elements in the sample space. Right, so here's the definition. Okay, PE means the probability of events. And remember that you should have learned that in possibly year 7, right? So all probability of any event will be between 0 and 1. Two extreme cases for probability of event equals 1, that means the event E is sure happening. So that means a certainty. For event E have probability 0, that means it is an impossibility. Right? So, and also you should have learned for probability of not E, that means E complements. So sometimes we use this symbol. Then you could use 1 minus probability with E. That actually means when you add up all the probability, the sum must be 1. Alright? And there's some interesting thing about using that complementary event. For example, if you are looking for probability of at least 1, then it will be easier for you to do 1 minus P probability of none. Okay, because the complement of at least 1 is none, right? Okay, for example, at least one student go to Brisbane, then the complement of that event will be none of the students go to Brisbane. Okay, so that's complementary event. All right. Okay. And then I'm going to introduce the idea of, okay, so sorry about this. Okay, I'm going to introduce you the idea of equal and unequal, equal and unequal likelihood. Okay, so for some sample space, all outcomes are equally likely to occur. In this case, if there are n outcomes, then the probability of each one will be 1 over n. Okay, so for example, tossing a fair coin. So if the coin is fair, then each outcome will have the same likelihood. Alright, so because there are two outcomes, so that means probability of head will be half, and probability of tail will be half. You see, they're equally likely, right? Tossing a fair die, so that means each number will be 1/6. Okay, picking one playing card out of 52 cards. Okay, so there are 15 cards. If you pick one of the cards out of them, right? So for example, if you get a heart, or I might use the figure here, so just easier to understand. Alright, so this is a set of playing cards, so let me pick one card. Okay, so that's heart 7. Okay, so if you pick this card, okay, then the probability will be 1/52, 1 out of 52. Okay, so that's what we call equally likely outcomes. Okay, but not all the sample space will have that kind of equally likely outcomes. Okay, sometimes they are not equally likely. Then how could we know the probability? You need to do experiments, including you collect statistics. Okay, for example, if there's an unfair coin, okay, or then possibly you get a greater chance to have a head or over that tail. Okay, and the achievement of Socceroos in the World Cup. So of course, the sample space will be like, okay, so for example, probability qualify into the tournament will be very high, will be 1 out of 2. Okay, but if you got going into the winning the champion, would be very, very low, possibly. Okay, so 1 out of 1 million. Okay, because we know that's Australian, yeah, not the strongest team. Okay, in terms of soccer, right? Okay, so you see that's the probability of each achievement will be very different. So that's what we call this is not equally likely outcomes. Brands of cars are served in the Bruce Highway. Okay, so of course if you see Holden, then the probability is quite high, possibly 1 out of 4 car. Okay, but if you see a Ferrari, I'm not quite sure of the spelling, possibly I'm wrong, possibly 1 out of 100. Okay, so if there are 10 brands of car, 10 different brands of car on Bruce Highway, you can't say each one is 1 out of 10. Some is much higher than that, some is much lower than that, right? Okay, so that's what we call not equally likely outcomes. Okay, so in our curriculum, you need to know how to deal with different types of sample space. If there are equally likely outcomes, then it will be much easier. You can do the counting and you can just add up all the number of outcomes. But if that's not equally likely outcomes, then you need to do a bit more in terms of getting the correct probability for each outcome. You can't just assume each outcome will have the same probability, right? So that's what I want you to be careful, to be aware of that ahead of new content. Alright, so let's do some very simple questions. Okay, so I know most of you possibly know how to do this. I just kind of revision, and also I put things into context to let you know. For example, it's a fair dice, so that means it should be outcomes with equal likelihood. A number less than 4. Okay, so if we got number less than 4, okay, so the event is less than 4. So that means you will get 1, 2, or 3, right? Okay, 1, 2, or 3. So there are 3 of them. Okay, so n of events, n of the sample space. The sample space, you got 6 numbers, 6 outcomes, right? So 6. And since they are equally likelihood, that means each outcome should have the same probability. And less than 4, you got 3 of them, just use 3 over 6, 1 for 2. But let me remind you that you must assume that the die is a fair die. If it's not, then you can't assume that each number has this equal chance to getting picked up, right? Okay, so a number less than 1. Okay, do we have a number less than 1? No, actually we don't have such a number. We don't have such we don't have a case where you toss a die and they give you a number less than 1. The smallest number would be 1. Okay, so in this case, the event will be empty set. So let me use these symbols to remember that. Since the events are empty set, so that means number of elements in the event will be 0. So probability of less than 1 will be 0 over 6. So that must be 0. Alright, number greater than 0. Okay, so we know when all the number you get from that die, so must be greater than 0, right? Okay, so this time, okay, we know that's the event, the set events just equals to the sample space, all right? Because all the numbers will satisfy the event, all right? So in this case, number of elements in the event will be equal to number of elements in the sample space, and that means 6. Okay, so this time the probability of that event will be just equals 6 over 6 will be 1. Okay, that's all right. So that's kind of, I introduce you how to use the just use that kind of symbols. Okay, possibly I don't want to confuse you. Let me change that less than E just into E. So E will be the event that's for the description of the question. So that's less than 1. Just change into the symbol E. Okay, so example 2 is another outcomes with equal likelihood. Okay, so there are 70 students join a reading scheme and they can choose science books or English books to read. Alright, and 43 students have read science books, 22 English books, and 20 haven't read either science or English books. Okay, if a student selects at random, find the probability that he or she has read both English and science book. Okay, so the probability is has read both. Okay, so that means you are going to find the intersection of two sets, right? Okay, so you need to think. Now you got some students have read science, some students English, but some students neither. Okay, and there are 70 as total, right? So you need to find how many of them have read both English and science book. Okay, so for this type of question, okay, so the events will be read both English book and science book, so that's the event. Okay, so here's the event. So event means set of students who have read both English and science. Okay, so that's the event, but how could we know how many of them? So you need to find NE. Okay, of course you've already know that's the universal set. Universal set will be 70 students, but you need to find number of students who have done that both. Alright? Okay, so it would be easier for me to explain if I draw a Venn diagram, because there are two different categories: English books and science book. So let's write this as English. So this is science. Okay, and that's universal set. We got 70 students. Alright, okay, let's see. So still remember the key to do this. The first part you need to find out is the intersection part, right? Okay, so if we don't have the number, just set it as X. Okay, so English you got 43 students, sorry, 32. Okay, so English you got 32 minus X, because totally they're 32. So just English, not science, 32 minus X. And similarly, you got 43 take away X, and there are 20 outside. Okay, so remember that all these numbers, when you add up, you need to have okay, so all these numbers add up, you need to have 70, right? Okay, so let's do it. So 32 minus X plus X, 43 minus X plus 20, which is 70, right? So when you solve it, you will see that X is 25. Okay, so that's 25. Alright, so let's think about, so that means number of students in the set E who have read both English and science will be 25. Okay, so the probability of such event E will be 25 divided by 70. Alright, so that's the probability you're going to find. Okay, 5 over 14. Alright, so if that's in paper 1, I think you need to express your answer in fraction, because you can't use your calculator, right? Okay, all good? Okay, so that's the way we do it. So for this type of questions, let me say again, if you see that outcomes are with equal likelihood, then it's easier for you to think about define the event and then find the number of elements in that event and use that number divided by the total elements, total number of elements in the universal set. That means the whole set of it. Okay, let me do one more with outcomes with equal likelihood. This time there are 30 boxes of apples in the market. The number of rotten apples in each box is counted, and the results are shown in the following table. Okay, so there are 30 boxes. Okay, and number of rotten apples. Okay, alright, so there are a few ways to ask the same question, but first of all, let me find out how many elements in the sample space. So the sample space should be all the boxes, so there should be 30, right? So add up all the number of boxes. Okay, so for A, the event is exactly one apple, so P equals NE over NS. So how many okay, how many boxes satisfying that event with exactly one rotten apples? Okay, so see, there are 4 of them. Okay, so number of boxes in that kind of in that event, you got 4 of them. 4 divided by 30. Yes, we use fraction. Right, and then how about the second? At least, oh sorry, that should be, sorry, that's a mistake, because that's at least one is not none. All right, so sorry about this. I just okay, so at least one, sorry, not at least one, exactly one, sorry about this, exactly one, so should be here, right? Exactly one, just overlook it. Okay, so exactly one, there's 6 of them, right? 6 of 30, so 1 over 5. Okay, B, this times at least one, okay, be careful of this. Okay, so for this one, okay, possibly it's easier for you to think about the complement of events. So if we say the event E is at least one, then the complement of event dash is none. Okay, so that means no rotten apple. Possibly I should write this way, no rotten apple. So event is at least one rotten apple. Okay, so let's see which one is easier, because we see that no rotten apple means 0. Number of rotten apples 0, there are 4 of them. But if you are going to find at least one rotten apple, because that's at least one, you need to add all the numbers. For one rotten apple, 6 boxes. 2 rotten apple, 10. You need to add up all 6 plus 10 plus 7 plus 3. Alright, so it's much easier to find the complementary events. Alright, so PE equals, we use that rule. Okay, we use that rule. 1 take away the complementary event of E, so it will becomes 1 minus 4 over 30, right? So it's like 20 over 30. Okay. Okay, so that's B. Let's do the C. At most, 1 rotten apple. So this time, our events at most 1 rotten apple. Okay, at most. Okay, at most 1. So it could be 0, it could be 1, but it can't be 2, 3, or 4, right? Okay, so this time, number of cases for at most 1 rotten apple. Okay, should be number of cases for no rotten apple, and number of boxes with 1 rotten apple should be 4 plus 6, be 10. Okay, so probability of that event equals this one, 10 over 30. Okay, so again, for this question is still each box have equal chance of being selected. Okay, so you can just find the number of boxes divided by total number of boxes. That will do it. So that's kind of thinking you need to develop for this type of question. When the sample space with outcomes with equal likelihood, that's kind of thinking you better develop. So it's much systematic for you to think and get your numbers and get it done. Alright? Okay, so then we look for another example. This time outcomes of unequal likelihood. So you see the unequal. So that means each outcome might have different likelihood. So for this one, we got outcome 1, 2, 3, 4, 5, 6. There are 6 different outcomes, but for this time, the die is a loaded die. Loaded means it's unfair, it's cheated. Okay, it's a cheating die. Okay, so for outcome, if you got 1, you got the chance 0.3. So 2, 0.2. So each one's different, and you need to find. All right. Oh, sorry, it's not frequency. Sorry, I need to change that. I will change that in my handout. So this is probability. Okay, sorry for the confusion, should be probability. Alright, so the probability is different. Okay, you need to find x. Alright, so that case is the event is 6. Okay, so let's say probability of getting 6 equals 1 minus, okay, probability not getting 6, not 6. Okay, right, so let's say probability getting 6 is x, probability not x would be the rest of them, and you need to take away all the numbers, add them together. Okay. Okay, so you would get 0.2 in this case. Okay, that's how we do it. Of course, you can think another way. You can think that, okay, all the probability add up should be 1. That's another way to do it, but I just try to use the complementary events to get you familiar with the case E and not E. Okay, probability of event equals 1 minus probability not E. Okay, so this kind of interesting thinking, right? So you can get around the question by using different ways. Right, okay, so okay, so that would be our example 5. Okay, so a tetrahedral die, so tetrahedral means a 4-phase. Okay, so it's a die in this way. Okay, so it's a die like this. So you might label some numbers onto it. 1, 2, the other side is 3 at the back, and here you might got 4. Okay, so that's the die. Okay, after some trials, it has been found out that the phase numbers 1 to 3 have the same probability. Okay, so phases numbers 1 to 3 have the same probability, but the phase number 4 has twice the probability. Find the probability getting 1 for 1 toes. Okay, so you need to find the probability getting 1. Alright, so because we don't have probability for any of the numbers, but you just know that relationship, right? So phases 1 to 3 have the same probability. That means we might think of this way. So probability getting 1 equals probability getting 2 equals probability getting 3. They all have the same probability for x. Alright, and probability getting 4 tries that probability, so that 2x. Alright, so again we understand this. So if we consider P4, it would be equals 1 minus P naught 4, right? So that means 2x equals 1 minus, so that 3x, x plus x bracket. Okay, so when you solve this, it should be 5x equals 1, x equals 0.2. Okay, so that means probability getting 1, 0.2. Okay, so again, for this question, each outcome has different probability. Okay, good. Right, so we've done 2 questions with unequal likelihood outcomes. Okay. Right, so let's do one which is, okay, so this one should be question example 6. Okay, so probability about areas. Okay, so sometimes we need to do the probability using the ratio of areas. Okay, so the general assumption is that each point in the area in concern should have the equal chance of being chosen or being hit. Okay, so for example, in the game, a dart needs to hit the shaded circle within a circular target. Okay, so here's the circular target. Suppose here's the circular target. Okay, the radius of a whole circular target is 20 cm. Okay, so the radius 20 cm, and depth of the shaded circle is 5 cm. Okay, so you got the radius of a larger circle and a smaller circle. Find the probability that price is won by throwing one dot. Okay, so you need to hit the shaded area. Okay, so assume the tip of the dot is of the point size. Okay, so the size is really small, just like a point, and you will hit the circular target. All right, so you must land within that larger circle. Okay, but it's not necessarily in the shaded region. So you are going to find the probability of hitting the target. All right, so price is on. Okay, so let's say that's the event. Okay, so this event actually means you need to hit the shade region. So that would be the interpretation of our events. Okay, so to hit the shade region, again you need to think about the ratio between the smaller circle and the larger circle, right? Okay, so it will be area of shaded circle, area of the shaded part, divided by the whole area. Okay, so that will be pi times shaded part, that's 5. And power square, of course, so I'm using 20 square. Okay, so after it's simplified, then we got 1/16. So that's the answer. All good? Okay, so again, for the area question, actually it belongs to the category of equal likelihood, because you assume each point will have the same chance of being hit. Alright? Okay, so basically for this video, I just reviewed some concepts about simple probability calculation by using the ratio between two numbers. Okay, so the numbers on the numerator should be the number of elements in the events. You need to think of that event as a subset of the sample space. Okay, and the numbers below would be the number of total elements in the sample space. Okay, you need to develop that kind of thinking, then it will be easier for you to get the answer quickly. Okay, possibly for some of you, you might still need more practice. So that's why I put all 10B and 10C together. So it seems a lot, but possibly for most of you, some questions are really easy. But for some of you, you still need to do more to get yourself familiar with kinds of the language you are using in probability. Then when it comes to the new content, you could adapt to the new content more easily. That's why you need to do this practice. Alright, so I put 10B and 10C together because basically you could use the same kind of method to solve most of the questions. Okay, so if you have any question, please send email to me. Alright, okay, see you next time. Bye.